All right, today is our machine learning session 4, and we're going to talk about decision trees. We've already talked about linear regression, we've already talked about logistic regression, and now we're going to talk about our first non-parametric model. So this is our first model that's actually going to be capable of solving nonlinear problems. And that is a decision tree. And a lot of people really like decision trees and because they're very easy to conceptually understand. When you look at them, they make sense. It's not as much math on the whiteboard as some of the other ones have been. They're very, very intuitive. And the reason we're learning about decision trees is actually so that we can understand a more generalized application machine learning model called random forests. So that's what we're really building to today, are actually random forests. But before we can understand the forest, we have to understand the tree. So here are decision trees. Just to start, it's a supervised learning algorithm. So we're still in the domain of supervised learning. We haven't moved to unsupervised learning. And you actually can build it both for classification tasks and regression tasks. In this case, for this remainder of this presentation, we're just going to focus on classification for how we understand this, but you can broadcast that to regression as well. What decision trees do is they split the data into subsets based on some feature. They look at something and say, I'm trying to predict if you're a cat or a dog, and maybe one question I ask is, are you over 50 pounds? And if you say yes, then maybe you're probably a dog, and if you say no, you're maybe more likely to be a cat, though it doesn't necessarily mean you are a cat. So you can kind of start to build this understanding of it. The goal is to continue asking. It's like playing 20 questions. If you guys have ever played that game, you're continuing to ask questions, and based on those answers, you're narrowing down to a result. So if they answer yes or no to a variety of earlier questions, you're becoming more and more confident about what you're going to predict. So what does this look like? Let's look at an example here. A decision tree at the very top, you're giving it all the information, and maybe you're asking it a question. You know, you're separating short and tall. If it's an animal, is it a short animal or a tall animal? And maybe if it's a short animal, you're separating, can it squeak or can it not squeak? So you can understand and make a prediction that, well, if it's short and it cannot squeak, maybe it's a squirrel. But if it's tall with a short neck and a short nose and it lives on land, maybe it's a rhinoceros. So you're following these paths down this tree in order to get to an outcome. Transforming this just a little more into like the machine learning domain, we typically rephrase these things as yes or no. So we don't, in the code, typically say short or tall. We'll just say tall ? And it's either yes or no. And if the answer is no, that's implied that you're tall. So here's an example with a heart disease data set. We want to predict if somebody is at high risk or at low risk for heart disease. So to this root node, which is the top node, we pass all of our data. This is one concept I'm going to say multiple times throughout this, which is that your data is broken into subsets as you progress down this tree. So there are smaller and smaller records as you progress down. So for example, we pass everybody to age. Then only people who are under 18 years old, only the records of individuals who are under 18 years old go to the left. Not all of the data goes to the left. A subset of the data goes to the left. Another subset, people who are 18 to 30, go down this center path. And another subset of people who are greater than 30 go down that right path. So now you've broken your data set into 3 smaller data sets. And in this, what they're calling a subtree in this picture, then we're asking another question. We're saying, are they a smoker for this data set, people over 30? And if the answer is no, then they're low risk. The answer is yes, they're high risk. If they are 18 to 30, we don't even ask if they're a smoker. It doesn't even come in. It's not relevant. This model determines they are low risk regardless. But if they are under 18 and they are greater than 60 pounds, then they are a high risk. So this is a great example of how machine learning algorithms, the decision tree algorithm works conceptually. What we're going to do today is understand, how does it choose 18? How does it choose 18 to 30 here? How does it choose greater than 30 here? How do we actually choose? Why did it choose smoker here and not weight? And why did it choose weight here and not smoker? We're going to understand how decision trees choose the feature to split on at each node. So generally, how decision trees work, and here I have some elements of a decision tree, extremely blurry picture, so I apologize. But at the top, this is supposed to say root node, I apologize. At the top, there is a root node, and then you branch into two different areas, and maybe there's a couple of questioning, maybe perhaps you could call them decision nodes, but there's a couple of different splitting criterias that further splits the data set. And then at the very end, you have a decision node that makes a recommendation, yes or no, 1 or 2, no heart disease or heart disease, or you could say apple or banana, or apple or pear. So at the end, you get to a decision node that outputs some probabilities associated with an outcome. So we start at the root node, we pass the entire data set. The data set is split into 2 or more subsets based on some features, and we separate that data. Each internal node represents a split or a decision, and then the leaf nodes, these are called leaf nodes. They're at the very end. The very last node, if there's no split, is a leaf, and that represents the final outcome of our prediction. So the question is, how do we choose the best feature to split on? So we have, okay, I was going to whiteboard this anyway, so I was looking at my slides. And let me see. Let me stop sharing, actually, because I think it will make my screen larger. Oh. Joe rocks. So, apples, bananas, pears. So, for example, we have some fruit. Let's just do 2. Let's just do apples and bananas. We have some data. And our data has 2 things. It has one X and one Y. So one feature and one outcome variable. And that is whether it's an apple or it's a banana. And there we go. Okay, we've got the 3 apples and 2 bananas. And the thing that we have is the color. So let's say apples are red and bananas are yellow. Sorry. All the apples are red and the bananas are yellow. So when we are creating our decision tree, sorry, swap back up 1. Slide here. So when we create our decision tree, we're passing all of our data to this first node here. And this is our root node. It has all of the data. And what we want to do is the goal is to predict either apple or banana. So when I say that we're passing all of our data to this, in training, when we train the model, we're passing X and Y. But of course, when we make our predictions at time of inference, we are just passing X. So we want our model to predict either apple or banana given just X. So tell us Y given X. So we pass all of our data, and the first question we have is which feature should we make a decision on? In this case, we only have one. We just have X. So we have to make a decision on color. And we're going to, in this case, we only have two categories. Is it red or is it yellow? And so that's the only question we can ask is basically red, question mark, either yes or no. And in this case, if it is red, then over here, this data set, now we have an apple, and an apple. And if it is not red, we have two bananas. And we would not proceed any further because we have perfectly separated our apples and our bananas. But this is what I wanted to represent is that the data follows those nodes. So over here we have just the apples, and over here we have the bananas. We don't have the apples and all of the bananas. Okay. That is okay. So what if we have more than one feature? Or what if we have more than two potential labels? What if we had red, yellow, orange, or I guess maybe more features is a better example. How do we split? How do we choose? What if we had color, but we also had shape, and we had weight of the fruit, and we had a bunch of other information about our fruit? How do we choose which of those features to actually split on first? How do we know which one's going to be the best at splitting? There are two common metrics that are used, and they are both very, very similar to each other. One is Gini impurity, and the other is information gain. You'll see later I call it entropy. So the beauty of machine learning algorithms is that there are going to be times when you have an opportunity to choose one algorithm over another within a specific model implementation. And this is one of those times. So we're going to talk about both of these, but know that you would just choose one method for choosing your splits at your nodes. So Gini impurity measures how often a randomly chosen element would be incorrectly classified. So you got a bag of marbles, and a lot of them are green marbles and some of them are blue marbles. Let's say you always predict it's going to be green. How often would you be wrong? If you just randomly pulled out a marble, how often would you be wrong? That's Gini impurity. How impure is your mix of labels that you're trying to choose from? Information gain is a reduction in the uncertainty after splitting, or a reduction in something called entropy. So entropy is the disorder in a system. And if we reduce that disorder, then that is we're gaining more information. So that's information gain. Note that it is important that the reason I am bringing these up is because they have different objectives you're trying to reach. So in this one, the goal is to reduce the impurity after each split. So you want a very, very pure thing. So your goal is you're working towards one. And whereas information gain, you're trying to reduce the impurity at each split. So you're working towards zero. I apologize. Information gain, the higher the information gain, better the split. The more information you are learning, so you're actually optimizing towards one. So they are prioritizing different outcomes. So it's important to know which one you are working towards. It really makes a difference when you see that value output, whether that changes your interpretation of if it's a good thing or a bad thing. All right, let's look through a very specific example. Let's try to calculate this, and maybe we'll walk through this one together, and then on the more complicated example, I'll just ask you guys to give a shot at this. We'll give it 5 minutes. Suppose we have a data set and we want to classify whether a student has failed an exam. Here's the data for a given node. For a particular node that we are at, 4 students have passed the exam, so 4 of them are A1, and 6 of the students are A0, so 6 of the students have failed the exam. How might we calculate the Gini impurity with that? I have the steps laid out there. How would we calculate the proportion of each class?
So the proportion would be 4 out of 10 and 6 out of 10, right?
Yes.
So then we square them.
And then we square them. And then we add them together. And then we take 1 minus that value. Yep. You have a number?
0.48.
0.48. 0.48. There we go. 4 out of 10, 6 out of 10. Square those numbers, add those numbers together, and we get 0.48. All right, do it again, but with 3 classes this time. How does that change it? You're like, I was still working on that one.
Typing it out is more of an issue than anything.
Actually, let me take a pause for one moment. If you're curious, if you are love to save time, and you wonder, we were learning a lot about programming in this class. I wonder if I can just program this solution, and let me hide the other solution. Sorry. There we are. Okay. This hides the other one. I just put it down there. So what does that look like when we try to code this, when we try to program this? This is what sklearn and other packages will already have been done for you, which is the really big advantage of using them. Let's create a function called Gini impurity. And to it, let's pass the students that have passed and the students that have failed. So in this case, we're passing 4 and 6. And when we pass passed and failed, let's follow our steps here. First, we're going to get the proportions of each class. Well, actually, first we're going to get our total because that's what goes on the denominator. So we're going to get our total by adding passed and failed together. So our passed is equal to passed over total, and our failed is equal to failed over total. And that is the same thing that we did in this step here. And now we're going to square our proportions. So let's go ahead and square those. In Python, that's 2 asterisks. So we're going to square those. And on the same line, we're also going to add those together. And we're also going to take 1 minus that to determine our Gini impurity. And of course, that's 4.48. So the nice thing is, if you do write it as a program, we can now change this we can see how this changes with varying numbers. So what if we change this to 6 and 6? How does our Gini impurity change? Well, that's 0.5, which is actually the worst Gini impurity that you can have. So Gini impurity actually ranges from 0 to 0.5, not 0 to 1, 0.5 being perfect mixture, which is not good because that's very, very impure. What if we change this to 0? 6, we get a 0 because that's perfect separation. You have a representation. This is 0. Our Gini impurity here is 0. Because this is one of those cases where we have 3 apples and we have 0 bananas. We have 2 bananas and we have 0 apples. And I can show you that in the code. All right, so we've got 0, you change this to past, failed, 1, 2, apples, bananas, it doesn't matter. We have 0, let's say we have 3 apples and 0 bananas. We get a Gini impurity of 0. We have 0 apples and 2 bananas. We get a Gini impurity of 0. So anytime that one of your categories is 0, when it's 2 categories that you're trying to classify, your node is all of one type. That is perfect. Of course, if it's 1 and 2, you're going to have a fairly high Gini impurity of 0.4. But if this was 1 and 10,000, you're going to be closer to 0. So you have, if you're imagining this like a bag of marbles and they're 2 different colors, you just want the proportion of one color to be higher than the other. So that is Gini impurity. Let's move on to our, like I said, our slightly more complicated example. Let's imagine we have 3 classes. Try giving a stab at calculating this one. What do you guys got?
0.62.
Nice. Okay, so we can also, I just want to show you guys the code that I was hiding earlier. Delete a few of these. Here it is. So if you notice, the only thing that we are changing here, that's a slightly complicated implementation, but essentially you could just do, we could add another category. So we could say P of category 1, P of category 2, and here we could add another category, P of category 3 equals, and the number of that over the total, and we would just, pass in category 3. You can essentially generalize all of that here, and instead just pass in our class counts for this, and we can sum that, and then we can take the count over the total to the power of 2 for count in our class counts. So we can loop over a list here. So we have this list, we can loop over that and say for each item in here, in case here we have 5, 3, and 2. So for each item in that list, let's take those to the power of 2 and then divide that by our total, which we're calculating as the sum of all the items in that list, and then take 1 minus that. So we've generalized that. Now, if I put, for example, 7, 8, the code still works. It's generalized to handle a list of any length, essentially. So we run this, and this is how we get our Gini impurity of 0.62 for if you have 3 things that you are trying to decide between. Okay. Any questions about Gini? Oh, yeah, one more comment here. So what does this look like? how does this actually look when we're trying to implement this, and how do we choose the best Gini impurity? Well, basically, we're going to run a lot of calculations, and this is why it's something that's really great to have a computer program run instead of us try to calculate this, because once you get to 10, 20, 30 features, and each of those features has lots of different categories with them, it really becomes unbearable to calculate by hand. But here's a situation where imagine we have 4 features to choose from. We're trying to predict something, maybe like the income of this person or something. Oh no, income's a feature. We're trying to predict whether this person's going to be approved or not, or something. So in this case, we have 4 features. We have their age, and we only have 3 categories for age. They're either a youth person, a middle-aged person, or a senior. We have their income, which is either high, medium, or low, and we have their student, yes or no, and the credit rating. What we would do in a decision tree is calculate the Gini impurity for each and every single one of those features. So we have these 4 features. So we'll say, what is the Gini impurity of that credit rating? And we're doing this the same way you guys just did for that yes or no example. We're saying, hey, we're going to split into 2 data sets. For when people have a credit rating, it's either a fair one or an excellent one. And in my data set, at this point in my node, wherever you are in your node, I have, when I look at those individuals with a credit rating that's fair, if it's yes, 3 of those are yes, they're fair, and 3 of them are no, they're not fair. And for excellent, I have 2 of those that are excellent and 6 that are not. And so you take these 2 Gini impurities and you average them. So this is my feature. These are values that my feature can carry. This is the Gini impurity of splitting on fair. This is the Gini impurity of splitting on excellent. The average of those is this. So 0.429 is the Gini impurity associated with credit rating. You can do the same thing here with student. They either are a student or they are not a student. You can calculate the Gini impurity and then calculate the Gini impurity for student. And just like we did in our 3 outcome example that we had a minute ago, just like we did for dogs, cats, and rabbits, in this case, income has 3 categories. So you would have 3 Gini impurities. You would average all 3 of those to get the Gini impurity for income. And the same with this age bracket. You would get the Gini impurity for splitting on age, is the average of these 3 impurities here. So you can see that this one is actually the best to split on from a Gini impurity standpoint. It is the lowest Gini impurity. Okay. Any questions on Gini impurity?
How did we get 0.62?
Oh, I know what you're saying. Because
Is it only that way for 2?
we didn't divide by.
Oh, you're probably right, it's only way for 2. Is that
I don't.
50-50 split?
Let me come back to this. I wonder if we were supposed to average and we did not. I wonder if we were supposed to divide by 3. Let me come back to that. It's a good question. I'll look at that on our break. Entropy, any other question? That's a great question. Any other questions on Gini impurity? All right. Entropy, similar concept, just slightly different mathematical formula in that this measures the amount of kind of chaos in the system. So this here is a very ordered system. This here is a very ordered system, but you can see there is chaos here in the middle. They're very mixed, not mixed at all here and not mixed at all here. So entropy measures the uncertainty or the disorder within a set. And if a data set this can sometimes be applied to other domains. So this is also applied in physics. But in our case, in our mathematical formula, if the data set has a perfect split, entropy is ordered, and the split is uncertain, entropy is higher. Okay, so this formula is our P, so that's our proportion, our probability, and then log base 2 is what we're going to use, so it's log base 2, and then it's log base 2 of the probability or of the proportion. So suppose we have a data set of students and we want to classify them based on whether they passed or failed an exam. So this is the same example we had earlier, where we have 4 students and 6 students. So you would calculate the proportion for each class. Remember, we said 4/10 and 6/10, and then apply this formula. And part of this formula is calculating the log base 2, and then sum the results. Are we ready? Slow. Okay. I'm sure you were well on your way to 0.97 entropy. So we have our proportion here. We're going to then plug that into the formula, which is that probability. Don't forget the negative sign. There was a negative sign here. Negative times the log base 2 of that probability, which this is the log base 2 for those probabilities. And so we plug that in here. It happens to also be a negative sign, which negates our negative sign on the outside, which is not surprising at all. And then we add those together, and that results in our entropy of the system. Okay, so let's look at that.
I'm trying to.
You are just
program
fine. Oh, that is fantastic. I will show you the answer. So you are probably well on your way here to, in our example of pass-failed, we have 4, 6, and we're taking in passed and failed. Again, we calculate the total like we did above. We calculate the proportion, which is passed over total, failed over total. And then if this, okay, so I believe log of 0 will throw an error for you. Let's just try it. So there's an edge case here to handle this error, math domain error. So cannot take the log of 0, so this will return 0 if that happens. In any other situation, we're going to calculate this with the probability times the log base 2 of this probability. So we have P passed here that we calculated as passed over total. You just take that times log base 2 of this, and you do the same thing with the failed. Failed probability times math log base 2 of the failed. And then don't forget your negative sign out here. we subtract these two things, we add these two things together, right? I don't know how I got the right thing that first time. Fairly certain we add those together. I will look at that. And we return the entropy, so 0.970. Sure why I have a minus sign here. In my head, this should be a plus sign. Okay, come back to that. So any questions other than that oddity on entropy and Gini impurity?
Does entropy have a range like Gini impurity does, or is it like anywhere between 0 to 1?
0
5
to 1, I believe. Yes. 0 would be that edge case where your probability was 0. I think it's 0 to 1. I have to think if it goes all the way to 0. But it goes up to 1.
Okay.
Up to 1. So Gini impurity and entropy are great things that you can talk about in an interview as you're interviewing for a data scientist position to show that you really do understand how a machine learning algorithm works. So one of the questions that I present in data science interviews is, hey, can you choose a machine learning algorithm, any algorithm of your choice, and walk me through that algorithm? And it's an opportunity for you to really showcase the depth of your knowledge. So you want to talk about an algorithm to the very depth you can. So if you choose a random forest, say, hey, random forests are made of decision trees, and this is a decision tree, and decision trees split at each node based on Gini impurity, and Gini impurity is 1 minus the probability of each class squared. So that would show that you really have a good understanding of and depth there. Okay, so I thought this was a really, really good example of decision trees for classification. And so we're just going to walk through it. If you guys would like, I'll share the slides. Definitely click on this person's webpage so they can get paid. So in this example, they have a data set here. So instead of apples, bananas, pears, we're trying to predict going to be an astronaut. You either are going to be an astronaut or not, and it's really based on your age and if you like dogs and gravity. So in this case, we're going to look at, what is it like to separate on a binary variable, and what is it like to separate on a numerical variable, because we haven't talked about that yet. We've talked about the binary one, and that's what we've done for our examples. But what if you have something like age? How do you split on that? You don't have 2 categories or 3 categories. You have potentially millions of categories. So how does that work? Well, first, this just walks through the decision tree and what that might look like. If they like gravity, true or false, then no, they're not going to be an astronaut. Or if they like gravity and dogs, then yes, they're going to be an astronaut. There's some terms here. If you missed those while we were talking about them or need a different way of thinking about them, this individual describes root nodes and branches, nodes, leaves, parent nodes, children nodes, maybe to more depth than I had in the slide. We'll talk about pruning a little later, so we'll come back to that. And this is another representation of Gini impurity. So it's always good to read other resources here, but we just talked about that. And so here's the first example I wanted to walk through. So we're creating a decision tree with, let's imagine we just have 2 binary features. So we're dropping the numerical one for this first example. We have a data set and we have 2 features. We have likes gravity and likes dogs. And how do we decide which of these two features that we're actually going to choose. Well, we essentially create two data sets. We create going to be an astronaut and their whether or not they're going to be an astronaut with likes gravity is true. And then we create another data set, whether or not they're going to be an astronaut, yes or no, with gravity is false. So when likes gravity is false, there's one individual who is going to be, or I'm sorry, there are no individuals who are going to be an astronaut, and there are 4 individuals who are not going to be an astronaut in that data set. When we look at like dog, okay, so let me stay on one example. So likes gravity here, so we would calculate our Gini impurity as 1 minus 5 over 5 plus 1 squared minus 1 over 5 plus 1 squared, which is 0.28 for this one. And this one is, of course, 0, because remember, anytime one of them is 0, that's perfect separation. That means everybody in this node is not going to be an astronaut. That means we have perfectly predicted, we've created a model that would, when it got to that node, be able to have 100% confidence that that person is not going to be an astronaut because they do not like gravity, is the feature that was decided on. Okay, so we have this other one, likes dogs, which the math is down here below, but we're doing the same thing. You separate into 2 data sets. If they like dogs and that are true, if they like dogs and that is true for them, what proportion of those people in that data set are going to be an astronaut? So in this case, there are 4 people that are going to be an astronaut if they like dogs, and there is 1 person that is not going to be an astronaut. Is 1 person that's going to be an astronaut that doesn't like dogs, and 4 people that do not. So then we calculate the Gini impurity for those, like you guys did on the slides. We average those together, we average those, and it's 0.32. That's what we did wrong in the slides. We didn't average them. We just added them together. Should be an average. I apologize. I'll fix that formula. So we average these 2 things together. So that's 0.32. And we see that 0.168 is a much lower number than 0.32. So of course, 0.168 is what we will choose. So we will split on likes gravity. So great, we split on likes gravity. Everybody who does not like gravity goes into this left node here. So let's say there were 4 people, I believe, that did not like gravity. All 4 of those people go over here. They don't go anywhere else in this tree. And this is something called a final node. In decision trees, they're actually a recursive formula. It means they will continue to call themselves and to build a deeper and deeper tree until they hit something called a stopping criteria. And one of the stopping criteria is a perfect split. So this node is a perfect split because there's no mixture. The Gini impurity is 0 at this node, as we saw up here, because it's not 0 for the average across these 2, but right here it is 0 at this node. And so we stop because the Gini impurity is 0, and we would then make an output decision and say, nope, this person will not be an astronaut. Okay, what do we do with the rest of the data? Everybody else who likes gravity, now we have to decide, what do we split on now? And in this case, where we only had 1 feature left, we of course split on likes dogs, and it's true or false, and then we just make the highest probability decision at that point because we don't have any more data or anything else to split on. But what if we did? What if we had 3 columns? Instead, we're not working with 2, we are working with 3. And what if we had to look at this age column? Remember I said we're going to have to learn how to split on numerical variables as well, such as age or price of a house. How would we do that? Well, we have to create bins to split on. And the simplest way you could do that is you just order these in order of ascending value is what they did here. So 24, 30, 36, we're going up in order. And then they took these two numbers and averaged them. So they grouped numbers that were similar in order to each other, took an average, and then these are the different categories. We're going to ask, what is the Gini impurity of splitting on 27? Greater than 27 or less than 27 for all of this data. Where greater than 27 would be 30 through 51, and less than 27 would be 24. So now we're going to calculate the Gini impurity across all of these numerical numbers. Of course, you could modify this algorithm so that you only calculated the average of only two averages, you know, one here and one here. And so you could make fewer possible splits is what what a good name to call these. These are possible splits for this feature. But here's what it looks like to calculate the Gini impurity for all of these potential splits, 27 through 49. So you can see at 27, we're saying, is it less than 27? Of course, there is only one value that is less than 27, 24. And there are, and because of that, there's only going to be one label in there. And the label is apparently no, for is not an astronaut. So of course that would have a Gini impurity of 0 because there's only one thing in there. You can see there are 9 potential categories that are greater than 27, but there's a split between 5 and 4 in terms of whether or not that those individuals are going to be an astronaut. So 0.49, which leads to an average Gini impurity that's not great. So as we look across here, we got 0.5, 0.5 as we start moving down that split, 0.48, 0.5, 0.475, 0.475, and 0.441. So out of all of those, it looks like our best splits are the top and the end, which is not very great because really you're just piecemealing one person out of. So you can already start to see some of the flaws of this algorithm. So you might put constraints on an algorithm, and you might say something like min samples at split, which means, hey, you can't just split one person off. That doesn't make any sense. You have to have at least 3 people for that to make sense. And that is something called a parameter, which we'll talk about a little later, which is we're getting into some very important concepts at that point of machine learning. But I think we're starting to really understand Gini impurity here. Let me see if there's anything else. So of course you would compare, if you had more than one feature to compare, we had likes dogs and age. So we had 2 features. You would compare all of the age options to all of the like dog options, which in like dog, it's binary, so we only have one option. So you can see how you would really have quite a few Gini impurity calculations to do. Okay. There is an implementation here in Python that shows you how to do this. This is, of course, very, very similar to all of the other models that you guys have built. So we're making our classifier here. In this case, you're going to call decision tree classifier, which we've imported from sklearn. We have our X variables here, which we're going to pass age, likes dogs, and likes gravity, which are columns within our data frame. And we're going to set our Y target variable to be going to be an astronaut. You're going to call your .fit function. You're going to pass X. You're going to pass Y. And that is going to fit your model. And you can plot a tree. You can actually, in sklearn, visualize what that tree looks like. And it will tell you your Gini at each of these splits and what your Gini was, how many samples existed at each split. And the top one tells you what the feature is you're splitting on. So we're splitting on likes gravity. When it says less than or equal to 0.5, that's just its way of saying yes or no on a binary feature. So you can see here, we start with 10 samples. 4 of them go this way. 6 of them go this way. We have 6 samples here. 2 of them go this way. 4 of them go this way. we have 2 samples here, one goes this way and one goes this way. So your data set moves throughout. So when you are calculating, what that means, when you are calculating the Gini impurity here, when we're saying, what's the Gini impurity of age less than or equal to 41.5, we are not actually comparing to this entire data set. When we're running our Gini impurity calculations, we're not running those on the entire data set. We're only saying what's the Gini impurity of age less than or equal to 0.5 for individuals who like gravity and individuals who like dogs. So for when the feature said liked gravity and liked dogs, so we're getting really conditional on that data set. So just on those 6 people, or on these 2 people in that case. Okay. Any questions so far on, I think that was really mostly it for decision trees. We're gonna talk about like pros, cons, advantages, disadvantages, but this is a good pausing point. Any questions so far? Okay. What you guys may have already picked up on is that decision trees, when it's just one tree, when we say decision tree, it's just one tree that we're fitting and we're deciding what those criteria are for pros and cons. They're really, really prone to something in data science called overfitting. That means when your model captures the patterns of your really specific training data set, and it doesn't generalize to a broader data set. So that example where we picked one off and it had the better Gini impurity, maybe if you gave it the exact same data, it would perform really, really well. But we don't want to give it the exact same data. We want to give it new data that comes in. So for example, if you are predicting whether a student's going to graduate or not, your model might get really overfit to your graduation class of 2024. And it might be really good at performing on 2024's graduating class, whether or not somebody's going to graduate. But you give it 2025's class and the same features and the same data, and it might perform worse. That's called overfitting. That means that it was really picking out very particular things about that class that don't mean anything to the general population. It means something for that class, but it's not a general statement you can make about all students graduating and their likelihood to graduate. So that's considered our unseen data. One thing that you can do to decision trees, I would actually just recommend you use a random forest, but we're gonna get there. What you can do to decision trees if you want to try to improve this algorithm is pruning. Now I just wanna talk about pruning because it's an important thing to understand and some potentials, because you can of course prune trees that are in a random forest as well. So pruning just means you take away some of those nodes. So maybe you looked through some of those decision nodes and you drop all the ones that have the worst impurity. And you say, nope, we're not even gonna use those. They weren't very good quality. And maybe you look at the ones that had only 1 or 2 like little pieces of data in them and you say, nope, we're gonna prune all of those. So that is pruning. Is when you like take some of those nodes and leaves out and kind of trim the tree up a little bit to not quite make it so overfit to your data set. You can of course do this during the process of growing the tree. Perhaps that's called pre-pruning, but really you would just set parameters within the tree. I'll show you guys how to do that in sklearn. That's like setting max depth. Your tree can only be this deep. Sometimes one of the things that happens is we create this really, really, really deep trees, and they're not always very good. So you can also do post pruning, like the one that I just mentioned, where you base it on that Gini impurity or predictive power. So people love decision trees. They're really easy to understand. They're very easy to visualize. A stakeholder comes to you and they say, why did you predict that claim would return to work? You can say, hey, it had this feature and they were, it was less than or equal to this, and then it had this feature and it was less than or equal. You can follow that tree down and you can tell them that very concretely, and it's interpretable. People understand it. It makes sense to them. It's really logical to follow. And this algorithm, in the past, we've talked about, logistic regression handles binary data, but not, scalar data, or linear regression handles scalar data, but not categories. This one can handle both. So it's one algorithm. There are regression trees and there are classification trees. And we've finally overcome our assumption on a linear relationship. So if you have non-linear features that do things in weird ways, like we talked about the cars, the relationship of the price of a car to the number of seats in a car, where it gets over a certain threshold of expense, this algorithm would handle a situation. It's capable of handling that type of situation. It really partitions the data into those categories. Okay, so we already talked, I was worried about talking about overfitting twice. Essentially, they become really overfit. They're really unstable. They can be unstable to changes. So if your data changes over time, they're not very resilient. And they can have bias to features with more distinctive values. And so, by the way, we'll talk more about overfitting in the next class, but this is just maybe a visual representation. You may think, oh, it performs really well in the data set. That's a good thing. Well, what it actually is doing is it's literally mapping like how to get from this point to this point to this point to this point to this. And that's not really what you want in an algorithm, because once you put in a new point in here, you got a new point, which is like, this is probably a fairly reasonable one. Your algorithm is going to be very, very wrong off of that. It's only going to be good at points that you've given it in the training set, which is not what we want our algorithms to do. We want our algorithms to generalize to unseen data. This maybe looks like it performs worse, but really it generalizes better to unseen data, because once you put another point in here, it's probably going to predict that with a much smaller error rate, especially at large. Once you put in more points, this one's going to have better performance than the other one. Okay. So some things that you can do is you can tune parameters. Okay, I talk about them in Random Forest more. So we've already talked briefly about a couple of them. You can set a limit to the max depth. You can say, hey, this tree can be no more than 15 deep, 15 nodes deep. You can say, hey, you have to have 3 samples in order to make a split. And not only do you have to, or maybe you have to have 10 samples in order to make a split, but not only that, but you have to have at least 3 samples at a leaf in order for you to make a decision. So that does away with that weird one-off scenario that we were talking about, min samples at leaf. These are all things that you guys can set in sklearn. So if we go to sklearn, Random Forest, here is your Random Forest classifier, and just like all of the things within sklearn, you can scroll all the way to the bottom here, and there should be some example code of how to implement it. So from sklearn ensemble, decision tree. I apologize. I realized we hadn't talked about ensembles yet, and that's when I realized that I was on the wrong thing. You can import your decision tree classifier from sklearn.tree. You can import your decision tree classifier. You can create your decision tree classifier, and then you can pass it to some sort of predict function. In this case, they're doing cross-validation. But these are the parameters that you can change on your model. When you instantiate that model, you can pass max depth. The default is none, which means that it will go on forever until it finds a good split. You can set min samples at split. The default is 2. You can set min samples at leaf. The default is 1. You can see there's many others. There's max features. There's min fraction leaf. And you might ask yourself, well, how do I choose a number? And how do I know that's the right number? And how do I know that's better than choosing a different number? And the answer to that is cross-validation. So what you do essentially is you train a whole bunch of models with a whole bunch of different numbers, and then the model that, don't mind me unplugging my computer, the model that performs the best is the one that you choose. So that is cross-validation, and that's what we talk about quite a bit in the performance, the metrics courses. How do you train a good model now that you know what these models are? How do you make one that performs well? So these are the types of parameters that you will be tuning in your models in that next course. And sometimes you'll see that these are called hyperparameters. That's kind of been a change in the field. That's not to confuse these when we talk about beta sub naught, beta sub 1, weights and biases. Sometimes people call those parameters. So they call these hyperparameters, which you set. They are not weights trained by the model. The model does not choose these. The model does not have a mathematical algorithm that chooses these. Those are parameters. These are hyperparameters. You select these based on the performance of the model. Okay. We are going to take a 10-minute break, come back at 7:27. Is 10 minutes too long? Does that seem reasonable? 10 minutes. 7:27. Then we'll, the bulk of this presentation was in, sorry, about half of it. The bulk of this presentation was in decision trees. Random forests are a fairly straightforward extension on decision trees. So if you understand decision trees really well, you'll understand random forests quite well. Okay, 7:27. Hey, Jean, I see your question now. How would you decide on what max depth to use? Did I answer that conceptually with cross-validation?
Yep.
Okay, perfect. Okay, the answer that we've concluded for the Gini impurity question about multiple classes, and this one being greater than 0.5, is that we applied the wrong formula to the wrong type of problem. So this is why knowing your metrics is very important and how these things work. Gini impurity in the form that we were discussing, this formula here, 1 minus the sum to n of p squared, probability squared, is only for binary options. So if you have a fruit and it's apple or banana, or you're trying to ask a yes/no question, that's the only time it's applicable. Otherwise, you have to use something called Gini gain, which is just a very slightly different transformation on that. And in that case, you're going to take the probability or the proportion. So if it's like 20% of them, you're 0.2 times 1 minus your proportion here as well. So kind of similar to what we did for entropy. So you would have 1/2 times 1 minus 1/2, for example, and then sum that across your different classes. I'll see if I can find a link and share that afterwards in the chat. Okay, let me stop this banner thing. Oh no, you can't hear me?
No, I can hear you now. I just saw like mouse was moving earlier, so I thought we were back.
Oh, okay. Whew. Oh, I see. When we were looking this up, that's right. Thank you. Let's. Back to random forest. All right, last 30 minutes here. Let's talk about random forest. So we know we have decision trees, and we know decision trees have problems with them. We know that they can be really biased, prone to overfitting. And there's this concept in machine learning, but it's really applicable like in the greater world. That's the power of the masses, the wisdom of the masses. So if you have, if I ask you, how tall do you think I am? And you'll give me an answer and you will probably be wrong. And if I ask all of you guys how tall I am, you guys all submit your answers. If I take the average across all of those answers, it's probably still wrong, but it's probably slightly closer to being correct. And if I asked 1 million people how tall they thought I was, I'd probably get the correct answer. So they're averaged across 1 million people answering that question, I'd probably get the correct answer. And this has been proven like time and time again through research papers, the wisdom of the masses. And random forest really takes that concept and applies structure. So applies an algorithm to approach that. So what if we didn't just have one decision tree? What if we had lots of decision trees and then we asked for the average answer? That is essentially a random forest. Now we have to introduce some randomness to it, because if we just built the same decision tree every time, we'd get the same answer, and that's not the point. We want different decision trees, just like we want different people to give us the answers. So we have to introduce some randomness. Okay, so a random forest is something called an ensemble method. This is our first ensemble method. And like neural networks are an ensemble method of sorts as well. An ensemble basically says it takes a bunch of different other machine learning algorithms, somehow decides to aggregate the output for that to make its final prediction. So an ensemble is just something that takes an input from a lot of other machine learning methods and somehow comes up with an output for a prediction, such as maybe just averaging those. So in this case, we have 3 different trees here. We have tree 1, tree 2, and then of course you could have n trees. But the interesting thing to note here is they are making different decisions. And not only are they making different decisions, they have different ways of getting to that decision. So you give the same data to all of these trees when you're asking for a prediction, when you're asking for a recommendation, and you say, what would you do? What would you recommend in this scenario? Is this a apple or is this a banana? And this tree says, oh, I'm going to go follow this path and decide it's an apple. Or this tree says, hey, I'm going to follow this path and decide it's a banana, et cetera, for all these trees. And then say you have 3 trees. You have 2 trees tell you apple, 1 tree tell you banana. You return your vote, your final prediction as an apple. I said 2 apples, right? Yeah, 2 apples, 1 banana. If I said that the other way, I apologize. 2 apples, 1 banana. You return it as apple with a probability of 0.66. So that is how your probability is calculated. It's just the number of trees that voted that over how many trees. So fairly straightforward if you guys understand decision trees to just extend to many decision trees. But we have to introduce some randomness. We have to make the trees different. They have to vary. Oh, sorry, I thought I was on a different slide. So why do we want to do this? Because decision trees are a terrible algorithm to implement. Don't ever put one in. Just do a random forest. It's less overfit. It handles larger data sets better. You're going to have better performance, and it's more robust to outliers and noise and that type of stuff. So wisdom of the crowd. This is the slide I thought I was on. I apologize. So we're going to have to introduce some randomness. We're going to have to make these trees different. How do we do that? We're going to do it in a couple of different ways. One, we are going to hand each tree a different subset of the data. This is called bootstrapping. So we're going to take our data, and it's in a giant bag, and we're going to shake it. We're going to grab a handful, and we're going to hand it to one tree. But we're going to take that handful back, and we're going to put back in the bag, and we're going to shuffle it again. We're going to take the handful out, and we're going to hand it to another tree. So we're going to do sampling with replacement. That means that if I could potentially give the same person to one tree. So I could be in a tree, in a data set that you hand to a tree more than once, sampling with replacement. So we sample, we put it back in the bag, and we sample again. And all of the trees will have overlaps in the types of data that they have. We are also going to, so we're going to do that bootstrap sampling. You'll see it later in the slides. We're also going to randomly choose features, subsets of features to hand to the trees. So subsets of data, subsets of features. And we're going to build out multiple decision trees. And then we're going to aggregate those predictions. Typically, there's many different ways you can do this. Just for simplicity, we're going to assume majority voting. That just means the answer that gets the most votes is the one that we return as correct. And the probability is simply the proportion of those answers in like a binary classification problem. In regression, you could, of course, do something very simple, like take the average, like the example I gave with height. Okay, so what is bootstrapping? So this is resampling of the data from a single data set and with replacement. Let me see if the next slide has a picture. It does not. So if we have a data set and there are a bunch of houses, we would randomly select a bunch of values from there. They could be even potentially selecting the same value. Say we select 30% of the data set, we would hand that to each tree, would maybe only get 30% of the data set. Oh, I had an example here, I apologize. So just jump down here to example. Here is what I am saying. Our original data set was A, B, C, D, E. These are some of the observations we had in our data set. Bootstrap sample 1 includes A, B, C, C, E, and Bootstrap sample 2 includes A, B, D, E. Notice that C is not at all in Bootstrap sample 2. So what this does, the reason random forests are resilient to outliers is because maybe there is like one feature that's heavily biasing your tree. It won't be in all of your trees. It will only be in some of your trees. So over time, the influence that that very biased feature, or I'm sorry, biased observation is having on your model, it's kind of smoothed out. It's not as much of a problem. It's not as influential because some of the times it doesn't exist in that data set. And when that doesn't exist, other features will be prioritized. So the next step, we build multiple decision trees. And I think I already talked about this, but they're going to make different decisions based on that subsample of data that they received in training. So there is a difference between training and prediction. When we are predicting with a tree, we give all the trees the same data to predict on, and we ask them to make a decision. But when we are training the trees, they all have different data. We give them different subsets, different slices of the data to train on. Let me see if there was anything else I wanted to say on here. In addition to doing multiple subsets of the data, like we had just said, like, hey, apples, bananas, pears, maybe we're gonna make 3 trees here. Tree 1 is, if this is A, B, C, D, tree 1 is going to get records A, B, C. Tree 2 is going to get C, D, A, and tree 3 is going to get A, C, D, for example. So not all of your trees have all of your data. They're going to have some subset of your data. In addition to that, the subset of data, subset of features. So also we're shrinking this way too. So we're shrinking this way, we're shrinking this way. So if we have, feature 1, 2, 3, if we have a house and we have number of bedrooms and we have square footage in the house and we have number of bathrooms, this one may receive number of bathrooms and square footage, but this one will receive number of bathrooms and number of bedrooms for that tree. So, and the features that you pass to the tree in training are the same features that you pass to the tree at inference. So even when it makes its recommendation, tree 1 will never look at number of bedrooms. It doesn't care about number of bedrooms. It's making its recommendation absent of number of bedrooms. And that makes these models extremely resilient, very resilient to features that play a lot of heavy bias or a lot of heavy weight in a prediction, and it allows us to understand net that feature, maybe what other features are bringing value to the model. So each decision tree, we just went through the algorithm for decision trees. They each grow independently they don't interact with the other trees. They don't decide how deep they're going to be based on how deep the neighbor's tree is. All of those parameters that we talked about are applied to each tree. So if we set the max depth for a random forest, each tree has a max depth, but they progress through to find their stopping points all by themselves. And until a node becomes pure. And typically we don't prune those. And then we just aggregate the prediction. So for classification, we said majority voting. Whoever had the most votes is correct. And we convert that to a probability. And then for regression, you could do something like averaging the values, for example. So the key thing to remember with random forest is it is an ensemble approach, which means we're combining multiple models. You're getting a lot of diversity among these trees because we're passing subsets of data and subsets of features to make these trees different in the way that they're making their predictions. And generally we expect that the more trees, if we have 100 trees, 500 trees, if we have 10,000 trees, that with all those subsets of data and all those different subsets of features, that it's going to make a pretty robust prediction. The really, really cool thing about random forest, one of my favorite things, is we can actually quantify the importance that a feature plays by looking at, okay, across all these different trees and across that all look very, very different, which feature is used most often for splitting? So which feature, even in the absence of all these other features, is most often used for splitting? And the one that is, and which one is used most often and has the greatest improvement in the model's performance, i.e. the greatest reduction in entropy, it makes the system more ordered. That is how we can very quantitatively define feature importance. So people like to say, what is the most important feature contributing to this like house prediction for a price? And you can say, well, it's bedrooms because this was the most important feature in the model. Or what's the most important thing helping this, for heart disease? Well, it's this feature. This person, whether or not they smoke, is the most important thing the model is using to make that decision. So even though it is a lot of different models added together, we actually can quantify which features are the most important. And again, it's non-parametric. So I label this influential parameters because if you go to look at random forests, which we will here in just a moment, there are a lot of parameters that you can put in there. And it's kind of overwhelming at times because we have N estimators and max depth and many others. Which parameters should you start with when training your model? Which ones are going to be most influential on the prediction outcome? And I can't say this for certain, but I know in my experience, these have been some of the ones that have driven the performance with substance. You can change a lot of other parameters, but then you're getting, it's like turning smaller and smaller knobs on your model. So these are bigger knobs. Here's your bigger knobs that can tune your model a little better. N estimators, when you see N estimators, that's just how many trees. Do you want 100 trees? Do you want 500 trees? Obviously 10,000 trees would be great. Just be aware that that's gonna take a long time to run. So you try to run that on your computer. I'm not sure when that's going to finish. So maybe start with 100 trees, maybe start with 50 trees. It's a reasonable place to start. See how quickly that goes. People typically do like 50, 100, 250, 500. Those are some of the parameters that I've seen in N estimators. Max depth, this is how deep you want your tree to be. Maybe you could do like 15, 34, 60 seems really deep, but it really just depends on how many features you have in your data set. So the more features you have, the more reasonable it is to have a deep tree. The less features, maybe you should do 5 or something, or 7. It just depends on how many features you have for max depth. Max number of features to be considered at each split for the node. So if you only want it to consider 5 features, or if you wanted to consider 100 features, and the minimum number of samples required to split a node from, so min samples at split and min samples at leaf. This is the one that we talked about. We found that weird edge case. This can just increasing these a little bit depending on the size of your data set. So that's what I'll caveat. If you have a really small data set, you probably can't afford to make these very high. So if you only have a data set of 100 records, requiring like 10 at a leaf might be too much, and you might not get a very good model unless you make it smaller. But if you have 10,000 records, you can put more onus on that and say, hey, there has to be at least 10. So some of these things you'll have to just kind of play around with, but these I've seen have been the most influential. Okay. Here's a picture of feature importance on the right here, by the way. When you get output from your model, this is what it might look like. It will be an order of your features. So these are some features an individual put into a model. And the most important feature is this random number at the top, followed by fair and age. So this is what that type of visualization might look like. There are some implementations of random forest, like XGBoost, that can actually handle missing data. So you don't actually have to transform your data. You just input it with empty values and it can handle that. Works really well for large data sets, non-parametric. can handle imbalanced data because of the way that those partitions work. Can be complex, and it can be harder to explain to stakeholders when they say, hey, why did it make this decision? And our response is, well, on average, sometimes this variable plays somewhat of an important role. So what I've done in the past to sort of get over that is explain that it's a wisdom of the masses, and I'll pull out a few example decision trees. So I'll pull out 3 trees, and I'll actually show them in each scenario what each of those trees would have decided. And then I extrapolate to that and say, hey, there are, of course, hundreds of these, and across all those hundreds of different trees, this is the output. On average, it said 0.8, 80% of the time, it's likely to be this scenario. And these are the features that we used as input, and these were the most influential and driving features to that. So it's less interpretable than a decision tree or a linear regression, for example, where I can say, well, it was 5 times the number of bedrooms. Okay, we are at time here. We have a few more minutes here. I'm going to pause the recording, and then I'm going to ask you guys if you have questions.